Hello, everyone. This is my very first time at the LongCon. It's been great. It's really good to see all these amazing presentations. So I'm going to talk about a project that I've been working on for a couple of years. It's called Storm. It is a cross-platform application that you can use to, well, not you can use, it's not done. You'll be able to use it to communicate over Tor with the aim of concealing metadata. So I've been working on it for a few years, ever since I started it kind of as a research project in my last year of university in the industry project. So I was doing research on what the different options would be for a truly anonymous messaging platform that doesn't release any metadata. One option is like using the Monero cryptocurrency and like embedding information in transactions. That's a bad solution. A better solution is to just use Tor. So in that project, I reached out to a Mozilla security engineer who had already completed most of the project. And I was working on the top layer of the protocol and also had to finish the bottom too. So I'll give a very brief overview of what the different layers do and how they work and why this is something interesting that people should use in the first place. So at the bottom is Tor, the onion router. It allows people to connect to hidden services over the Tor network, which means that no one observing the network knows who you're connecting to. The Bramble rendezvous protocol is the next highest layer. It just uses Tor to create onion services. It essentially just abstracts over it. You provide it with your own private key and the peer public key that you're trying to connect to, and it'll create a TCP-like connection for you that it can provide to a higher protocol layer. The Bramble transport protocol provides integrity, concealability, authentication, and forward secrecy. It's a bit redundant because the TCP connections over Tor are already kind of concealed. Whereas the Bramble synchronization protocol uses the lower layer to synchronize graphs of messages between peers. So the goal of all these is that when you combine them together, you could create an arbitrary peer-to-peer application that uses Tor. Since the interface of the Bramble synchronization protocol, it uses the terminology of messages, but to it, messages are just binary strings. What they actually mean and how they're used is up to the consuming protocol. For Storm, it'll just be text messages, but I've got an example later of what an implementation of a file system would look like. So why would one care about an anonymous messenger? So there's a lot of applications out there that provide security guarantees. There's Signal, Telegram, various applications that use the Matrix protocol, mainly Element. But I haven't really seen one that gives meaningful guarantees about how hidden the metadata is. I'll discuss later how Signal tries to do it and why I think that's not a sufficient approach. But yeah, so the whole reason you would use it is to conceal your metadata. There's also maybe some benefits of the fact that Storm uses a Rust implementation of the Bramble protocols. There's already a Java implementation that already exists. They are used in an application called Briar, which was published in 2018. One benefit of the Rust implementation is that it would be able to use RT. RT is the Rust implementation of the Tor project. which is an ongoing effort and isn't quite ready for production use of onion services, but they're getting close. The goal is eventually that RT will completely deprecate the Tor project. The C implementation, that is. But why should you even care about metadata? Well, let me tell you about graph theoretic social network analysis. So, the security of message content, that's non-trivial. It's useful that applications like Signal are able to provide that. But metadata on its own is still very useful. There are like a lot of cases of states or like corporations gaining access to metadata or other forms of data with the goal of constructing models of networks between people, like having an idea of what communities exist and how they communicate with each other. Some forms of analysis are analyzing the centrality of specific people. For example, if there is a node in the network that has a high degree of connectivity, then that might be a leader in the community. Or there's also bridge centrality, where between two different clusters of nodes are people. If a node has high bridge centrality, then targeting that node might separate different communities. The whole point being, you can use the models of networks of people to stifle dissent. You can also have other uses, such as marketing, propaganda campaigns, like Cambridge Analytica, for example, a few years ago. Graph analysis was part of what they did when they were trying to do propaganda campaigns to influence political movements. They weren't doing it with metadata alone. There's a lot of different information, especially social media information, that you can use to construct social network models. But my point is that we should try to avoid any form of information that can result in constructing such a model. Metadata is one such source. So contact chaining is another example of a form of analysis. You may have heard that very recently some like American law enforcement groups were like doing social media analysis. They would identify suspected gang members, and then based on that identification, they would suspect anyone they're associated with of also being a gang member. And they would do this to like n degrees of separation, with the result that they could suspect thousands of people of being a gang member, which should be frightening if you're like me and you're a bit concerned that a political situation is developing where the line is getting blurred between genuine targeting of organized crime versus developing campaigns of terror against marginalized people. Edward Snowden also leaked in 2013 the many different programs of the NSA to get information including metadata, to develop these social networks, models of social networks. And we should make that harder for them. So Signal has a feature called sealed sender that they say helps to conceal metadata. I'm not very convinced. How it works is on the user's device, they first encrypt their message, and then they add a second layer of encryption where the sender ID is included. So they send that to the Signal servers. And then the Signal server at the application level does not have access does not have access to the sender ID. They only know where the message is going, not where it's coming from. And then the receiver receives the message. They can decrypt the first layer and the second layer, so they have the message and they know who it's from. The trouble is this works only at the application layer, But these are still just TCP connections. So they can get the IP address, and you have to trust that the signal servers are following the policy that they say that they have, that they're not logging IP information, and you have to trust that they're not compromised in any way, either legal or illegal methods, through like coercion by the state or infection by malware. Maybe that amount of trust is acceptable to you. To me, it's not. I'll state that more definitively. It shouldn't be to you either. So I'm going to go into a bit more detail for as long as I have time. I haven't like timed out this presentation at all. So I probably don't actually need to go into how Tor works. The main point of the protocol is that it abstracts over all that. But basically, the Tor network is very large. It has thousands of nodes. And it conceals metadata by transmitting data over a sequence of hops. Any particular node doesn't have all the information. Only the last node can see the data that's actually being transmitted, unless it's encrypted again, such as with SSL. And only the last node can also see where the data is going. Only the first node can see where it's coming from, but unless you are doing a massive de-anonymization attack against the whole Tor network, or by some other method, there's been a lot of research about how exactly this can be done, then you're probably not going to have access to that metadata. I think how exactly de-anonymization can occur is a very interesting topic. There's been a lot of research. It's worth looking up, but I think as far as the different options for concealing metadata, this is probably the best one. There's two main ways of using the Tor protocol. You can either use it to access a normal website, like a website in the clear, in which case there's only 3 hops. The other method is by establishing and then connecting to an onion service. Now that's a whole lot of complexity that it's on the next slide, but I probably won't explain it. But basically what a hidden service is, hidden service and onion service are interchangeable. The new term is onion service. Essentially, it's just a web server. When you're visiting a darknet website, either to visit a secret forum or buy some commodity, on top of the onion service connection, which is TCP-like, it's just transmitting HTTP requests and static web files on top of that. But it doesn't have to be HTTP. It can be arbitrary data, which is what these protocols are doing. This is how you set up an onion service. So now you know how to set up an onion service. Let's talk about the Bramble rendezvous protocol. So this is just a diagram of Diffie-Hellman key exchange, which is most of the complexity. Essentially how it works is over some other medium, you and the peer you want to connect to exchange public keys, and you keep your secret keys to yourself. The paint metaphor is kind of illuminating, but basically how it works is you mix their public key with your private key, and you can create a shared secret. So you and the peer both have the same secret. It's just a string of bytes, and no one else has that secret. So now we're over here. Got a common secret. How Bramble Rendezvous Protocol works is it breaks this secret in half, and the first half is Alice's onion URL. The second half is Bob's onion URL. An onion URL, if you've ever been to a darknet website, is the random string of letters and numbers that allows you to connect to an onion service. It's also just a public key. So both peers spin up an onion service using the two onion URLs that they calculated from the common secret. And so the two onion services are up. No one else knows that they're up. No one else knows the URL. They're both trying to connect to each other. Eventually, one of them will succeed, and the Bramble Rendezvous Protocol ends. and provides that connection to whatever protocol is consuming this protocol. So I'll try to avoid talking about this one in too much detail, because this is the really cryptographically interesting one that would take a long time to get into. But essentially, this protocol isn't necessarily using the rendezvous protocol. It's compatible with multiple different protocols, such as it can communicate over Bluetooth, over Wi-Fi. It's designed to be able to communicate over disks sent in the mail. It provides confidentiality, integrity, and authenticity. The way it provides authenticity is that this protocol communicates in sequences of streams. A stream has a tag and a header and one or more frames behind it. The frames contain the actual data. The tags at the start can be calculated in advance based on the stream number, I believe. It says right there. So based on the shared key that they have to communicate and the stream number. So these can be calculated in advance, and you'll calculate like 10 or so for each peer, and then when you receive a stream, it'll have a tag, and you can see whether that tag is in the list of the ones you pre-calculated. If it is, then you know who's trying to communicate with you. If it's not there, then discard the stream. Yeah, and then the header, basically, it just similarly contains an encrypted ephemeral cipher key. So that cipher key is what actually encrypts the data that you're actually trying to communicate, which is in the frames. That's enough detail. So the top layer of the Bramble protocols is the sync protocol. This is the first layer that is actually part of the application layer. It has two concepts, basically, groups and messages. Groups have just a string description. That's what identifies them. And messages belong to a group, and a group can be modeled as an acyclic directed graph of messages. So the sync client is passed a Bramble transport protocol socket, and it is receiving data constantly when there's messages being sent. So it's got a wire protocol. It's probably not that interesting. If the sync protocol receives a message from its client, then it will ask the client, what peers am I supposed to share this message with? It'll send offer records to all of the peers and possibly receive requests back. If it receives a request, it sends the actual message. The message is then acknowledged. Yeah, so as far as the sync protocol is concerned, all these messages are just binary strings. It delegates validation to the client of the sync protocol, which is the actual application that you're writing. So the sync client validates that a message is something that it can understand and extracts dependencies from it. So where messages are organized into graphs, the dependencies represent the messages that are higher up in the graph. So although the messages might arrive out of order, a message's dependencies will always be delivered to the client first. That might have seemed a little bit abstract, so here's an example. There's kind of problems with this design, but bear with me. This is how you might implement a file system using the Bramble sync protocol. So Alice decides that she wants to share some videos, so she creates a group with the title My Videos, but the description is just this whole string. She adds the film Seven Samurai and invites Bob to watch her movies. Bob accepts the invite, and the acceptance of the invite has the invitation itself as a dependency. So if someone else joins this group, they will see that Bob is invited and that Bob joined, and now they can share these messages with Bob. So this is actually very similar to the BitTorrent protocol. Essentially, Alice has declared that the movie exists and has also uploaded the different segments of data that together compose the whole movie. And then also transmits another message that has all of these segments as a dependency. And yeah, by receiving this one, you know exactly which segments. Wow, I'm almost done. Yeah, by receiving this one, you'll know which segments are part of the movie, and you can then stitch them all together. I think that is the last slide. That was way faster than I thought. Any questions?